Okay, so this is lecture 5.3, or rather section 5.3 from the text. It's entitled Higher Order Derivatives, Acceleration, and Concavity. So for the most part of this lecture, we're going to be focusing on the second derivative. So what we're going to do is I've broken it down into pieces, and I'm thinking of probably making a separate video for each one of these, depending on how long each one will be. So there will be a collection of videos all combining to create section 5.3. So the first thing is going to be just taking second derivatives, just practicing taking second derivatives. Then we'll do a physical example, like a physical interpretation of what a second derivative is, looking at acceleration. We'll do a business example, so an interpretation of the second derivative in terms of finances, and then we'll look at some geometry, because the second derivative has a lot of interesting applications in basically the shape of a graph, concavity. And then we'll do some real-world examples. We'll look at a new test called the second derivative test for extrema values. And then we'll look at even some higher order derivatives, third, fourth, fifth, etc. Higher order derivatives and how those are used in calculus and in the real world. Okay, so first thing I'm going to do is just walk through a bunch of examples of taking the second derivative. Basically, the way you take a second derivative is you take one derivative and then you do it again. And it's really that easy. So this is going to be a great review for first derivatives too, because to get to a second derivative, you've got to take a first derivative. Okay, here we go. So let's start with some polynomials, because they're the easiest functions to take derivatives of. F of x is equal to 3x to the fourth plus 2x squared minus 7x plus 6. The instructions are to find. Now let's talk about notation real quick. There it is. Okay. This is the second derivative of f. If you remember, we use a little tick mark to denote a derivative, so we're going to use two tick marks to denote a second derivative. Alternatively, for the df dx notation, we would say for a second derivative, well, here's a first derivative. That's a first derivative, the derivative of the function f with respect to x. When it's a second derivative, you put a little 2 there and a little 2 there. Okay, so let's find the second derivative of f. I'm going to use this notation for this problem. F prime, so first you find the first derivative, power rule. Okay, so this will drop down. The form will become a coefficient. So I'll have 12x to the third, and then plus, that's a 2 there, so this will be 4x. And then minus 7, and that 6 goes away. Okay, so just standard power rule there. And then the second derivative, now I just take the derivative of this new polynomial. So I'm going to drop the 3, I'll have 36x squared plus 4, and that's it, because now this 7 goes away. This is it. That's the second derivative. Okay, let's move right along. Let's say g of x is equal to another polynomial. We want to find, and I'll use this notation this time. So the second derivative of g with respect to x. Okay, so here we go. dg dx, the first derivative of g with respect to x, is 34x, just dropping the 2, and then plus 6. And now the second derivative, just going to take a derivative of this, and the 6 will go away, and I'll just be left with 34. So that's a constant. Okay. Number 3, h of x is equal to x plus 1 over x. So we've got a polynomial plus a rational function, and we want to find h double prime of x. Okay, h prime of x, first derivative, that's going to be 1, because the derivative of x is 1, minus 1 over x squared, because the derivative of 1 over x is negative 1 over x squared. Okay. The second derivative of h, this 1 is going to go away, so I need to think about the derivative of 1 over x squared. So the derivative of 1 over x squared, let's see, that 2 would be negative, drop that down, so would be positive 2 over x cubed. Positive 2 over x cubed, because what's happening here is I'm saying the derivative of negative 1 over x squared, well, that's the same as the derivative of x to the negative second power, well, negative x to the negative 2. Remember that the power in the bottom here for a rational function is the same as a negative exponent, derivative. So I haven't taken the derivative yet. Then I would drop the negative 2 down, so I'd have, negative of negative 2. So now I'm taking the derivative, dropping that negative 2 down, and taking the power down by 1 would take me to a negative 3. Negative, negative cancels, that leaves me with a 2, and x to the negative 3 means x to the third in the bottom. So there we go. And the 1 here, the 1 just disappeared. It's constant. You take the derivative of a constant and it disappears. It's 0. Okay, let's try another rational function. Let's do negative 3 over x squared, and let's find the second derivative. Okay, so first derivative. I'm going to do a similar thing. This is this is pretty much the same thing, except there's a negative 3 up there instead of a negative 1. So I'm going to have positive 6 over x cubed, positive 6 over x cubed, because the negative 2 will drop and multiply by that negative 3, becoming a 6, and then the exponent will come down by 1, making that a 3. And then the second derivative, so now I'm taking a derivative of this, and it's going to become negative again. It's going to become negative again because this negative 3 here, this exponent is a negative 3 because it's in the denominator. It's going to multiply by that 6, become negative 18, and the power will drop. The power will drop. When I say the power will drop, that means it gets bigger in the denominator. So what's happening here is six over x cubed, the derivative, is the same as 6 times x to the negative third. Still haven't taken a derivative yet. Now I'm going to take the derivative, so I'll say 6 times, drop that negative 3, take the power down by 1, but that's just the same as negative 18 over x to the fourth. Okay. Okay, 5. Number 5. Let's do some radical functions. So we've done polynomials and rational functions. Let's start with let's try a radical function, square root of x. Let's find the second derivative of q with respect to x. Okay. First derivative, so dq dx. dq. Oh, by the way, the little 2's here, why is that one there and that one there? Well, a first derivative is, for a function with respect to x, is d dx, right? And then I want to take another derivative, d dx, right? So a derivative of a derivative. You can think of them, these operators, these derivative operators, as multiplying onto each other. Without getting into too many details, it's okay to think of them like that. So 2d's on the top is d squared, and 2dx's in the bottom is dx squared. So technically this whole thing is squared there. And then you just tack on whatever the name of the function is. Whatever the name of the function is, we put it right there. Okay, so first derivative of q with respect to x. Well, we know that square root of x is equal to x to the 1/2, right? Got to know these exponent rules. So drop the 1/2 to the front as a coefficient, and then take the exponent down by 1. 1/2 minus 1 is negative 1/2. And if I want to clean this up, this will be the same as 1 over 2, right? That's the 1/2 there. That's the 1/2. And then x to the negative 1/2 means square root of x, but it's in the bottom. So there we go. Alright, now the second derivative, so d squared q over dx all squared. So now I'm going to take the derivative of this. So maybe to take the derivative of it, more helpful to think of it in this form because it's already written in its exponent form. So looking here, I'm going to drop the negative 1/2, multiply it by this 1/2, so I'll have negative 1/4. 1/2 times negative 1/2 is negative 1/4, and then x. Now I want to take this exponent down by 1, so I'm going to subtract 1 from negative 1/2, so I'm going to do negative 1/2 minus 1, but that's just negative 3/2. There we go. And then cleaning this up, I'm going to have a negative 1 on the top and a 4 in the bottom. That's the negative 1/4. And then this is a square root because of that 2 there. The denominator should be the index of the radical, so it is still a square root. But it's not just square root of x anymore, it's square root of x cubed. And why is it in the denominator? Well, because the exponent is negative. Okay. Let's do another radical equation, or a function. M of x is equal to cube root of x over 4. So that's a 3. That's a cube root of x over 4. Let's find the second derivative of m. Okay. Cube root of x over 4. First derivative, m prime of x is going to be equal to, well, we need to remember that cube root of x is equal to x to the 1/3. So I'll drop that down, so 1/3 x, and then I need to subtract 1 from that, so 1/3 minus 1 will be negative 2/3. So this will be negative 2/3 all over 4. And we can clean this up a little bit. Let's clean up these coefficients first. This is 1/3 times 1/4, so this will be 1/12, and then times x to the negative 2/3. And then that can clean up to 1 over 12, and then a cube root of x squared. Okay, now let's take the second derivative of this. So now we need to take the derivative of this first derivative. So let's look here because this is already set up. It's already in exponent form, so it should be easier to deal with. So we're going to drop the negative 2/3, multiply by this 1/12, so that's going to give me negative 2 over, so the negative 2 multiplied by the 1 give me negative 2. 12 times 3 is 36. And then I need to take 2/3 down by 1, so I need to do negative 2/3 down by 1. Negative 2/3 minus 1 is negative 5/3. And that is my new exponent. And then finally, this can clean up to negative 1 over 18 times the cube root of x to the fifth. Negative 1 over 18 is coming from negative 2 over 36. That just simplifies to 1 over 18. And then the negative 5/3 in the exponent corresponds to a cube root of x to the fifth in the denominator. Alright. Okay, so continuing with these examples, I've done 2 polynomials, 2 rational functions, and 2 radical functions. So let's do some exponential functions. Let's say n of x is equal to 5 to the x plus 3x squared. So we've got a polynomial, 3x squared, but also an exponential function here. Let's find that second derivative of n. Okay, first derivative of n. Well, we got to remember how to take the derivative of an exponential function that has some base 5 here in this instance. It's just going to be the, well, here we go. The derivative of b to the x is just ln of b, whatever that base is. So that's the natural log of b times b to the x. Times b to the x, where this b, in our case, is 5. So we have ln of 5 times 5 to the x, and then plus the derivative of this polynomial, but that's easy, it's just 6x. Just 6x. Second derivative, so now I'm going to take the derivative of this. Now what's going to happen here is ln of 5 is just a constant. It's just a number. It's just a number. So basically, I'm going to ignore it, kind of tack it on to whatever the derivative of this is, but remember the derivative of this is going to be, so here's the first ln of 5, right, that's just that coming down, and then times another ln of 5 times 5 to the x. So the first ln of 5 comes from the first derivative, and then when I take another derivative, the derivative of this exponential function throws in another natural log of 5, and then plus 6 for the polynomial. So when you're taking derivatives of exponential functions with base b, if you keep taking derivatives, you're basically just going to keep copying down the exponential function itself, the 5 to the x, 5 to the x, 5 to the x. You have one of those in each derivative, but you keep tacking on an extra factor of ln of the base. So I could clean this up a little bit, I suppose. I could write it as ln of 5. I could write it as ln of 5 all squared, I suppose, times 5 to the x plus 6. Okay, let's do another one. Let's do a natural exponential function. So let's say p of x is e to the 2x. So a little bit of chain rule going on here, because I've got a function inside of my exponential function. So I'm going to say first derivative of p is going to be the derivative of e to the x is just itself, just e to the x. But since I've got a function up in the exponent position, I need to think about using the chain rule. So I'm going to do the derivative of the outer function, which is the e to the x function, with respect to the inner function. But that's just going to be the exact same thing. It's just going to be that. That's the derivative of the e function with respect to the inner function. That's it. Then times the derivative of the inner function being the 2x. But what's the derivative of 2x? It's just 2. So flipping this around, there we go. Now the second derivative, I'm going to take the derivative of this now, but it's the same thing is going to happen. I'm going to have this 2 hanging around, and I'm going to drop another 2, right, because I'm going to use the chain rule again, so I'm going to have that 2 times another 2 from the chain rule, and then the e to the 2x, so I'm getting 4e to the 2x. So you can see that when you've got an e function with just a linear exponent, it's just going to keep dropping that that number down each time you take a derivative. Just keeps dropping that number. So if I took another derivative, I would have 8e to the 2x. And if I took another derivative, I would have 16e to the 2x. Okay, but we'll talk more about that later when we do higher order derivatives. Alright, let's do some log functions now. 9, where is it? Let's use a different notation here. Let's say we don't have a function, but we just have an equation. Y equals 2 times log base 3 of x. Find find the second derivative of y with respect to x. Well, dy dx. This is a log function, so let's recall that for a log base b of x, the derivative is, I'm out of room here, let's see. The derivative is 1 over x within, 1 over ln of b times x. So similar to the exponential in the sense that it has an extra factor of that natural log of b, of that base, but it's a different derivative though. Overall, we say the derivative of a log is going to be 1 over x with an extra factor of that ln of the base. Okay, so here, the 2 is just going to get carried along. I'll just go ahead and put the 2 on the top, and I'm going to have natural log of 3 times x. Okay, second derivative. D squared y over dx all squared. Okay, so now I need the derivative of this. Now, I need to keep in mind that 2 and ln of 3 are just numbers. They're just going to get carried along. In fact, I could even go ahead and write them down. They're just constants. X is the thing that I'm actually taking a derivative of, and it's 1 over x here, right? This is 1 over x. This is x to the negative 1. So when I take the derivative of x to the negative 1, I drop that exponent down, which is just going to have the effect of making that 2 negative, and then take my exponent down by 1, so I'll have x squared. Just like that. Just like that. So this is just some number. This is some number attached to 1 over x. And remember, the derivative of 1 over x is negative 1 over x squared. So the negative coming there, and the x squared there. Okay, number 10. R of x is equal to ln of 2x. Find r prime. Find r prime, double prime of x. First derivative, well, ln of x, the derivative of ln x is just 1 over x. It's just 1 over x without that extra factor of ln of the base. Technically, you could argue that it is there because the base of a natural log is e, and ln of e is just 1, so it's technically there, but doesn't need to be written down because it's just going to be, this factor will just end up being 1 for this particular logarithm. So we're going to have the derivative of the natural log is just 1 over x, but we don't have just an x as our input, we have a 2x. So we're going to take the derivative of the outer function, which is the natural log, with respect to the inner function. So instead of 1 over x, it's 1 over 2x. And then times the derivative of the inner function, which is 2x. So the derivative of 2x is 2. So it's just going to be 1 over x. 2's cancel. That's strange, but that's how it works. Now we want to take the derivative of 1 over x, but that's just going to be negative 1 over x squared. There we go. Alright, we did 2 polynomials, 2 rational, 2 radical, 2 exponential, and 2 logs. Now, the last 5 examples here are going to be just more complicated examples, more complicated problems involving more involved chain rule and product rule and quotient rule. Let's say f of x is 2 times some polynomial 3x plus 5, all cubed, and let's find the second derivative of f with respect to x. Okay. The first derivative is going to be the derivative of the outer function with respect to the inner. So the inner function is going to be that 3x plus 5, and the outer is going to be, if you replace that inner with just an x, we're left with 2x cubed. Okay, so the derivative of this is going to be 6x squared, but we say with respect to the inner. So we don't just write 6x squared, we write 6 times this whole thing squared, and then times the derivative of the inner function. This is derivative of the outer with respect to the inner, then times derivative of the inner, which is just going to be 3. So we have 18 times. There we go. Now the second derivative it's going to be a similar thing. We're going to take the outer well, we could reestablish what the inner and outer function are, but sure, we can do that. Okay, inner function is still 3x plus 5. The outer function now, replacing 3x plus 5 with just an x, is going to be 18x squared. So let's take the derivative of this. It's going to be 36x, right? But x is 3x plus 5. So that's the derivative of the outer function with respect to the inner function. And then times the derivative of the inner function, that's going to be another 3. So altogether, we're going to have 3 times 36 is 108 times 3x plus 5. There we go. Okay. Number 12. Let's say g of t is equal to square root of 2t squared plus 3t minus 4. Find the second derivative of g with respect to t. So this time the input variable is t. Okay. First derivative, dg dt. Okay, so I've definitely got an inner and outer function here. My inner function is that 2t squared plus 3t minus 4. My outer function is the square root of t, just replacing that entire inner function with t. Now the derivative of my outer function is going to be 1/2 times that inner, or with respect to the inner, and then raised to the negative 1/2. That's the derivative of a square root function, so I need to write in my 2t squared plus 3t minus 4. There's the derivative of the outer with respect to the inner, then times the derivative of the inner. So the derivative of my inner function is going to be 4t plus 3. 4t plus 3, that's the derivative of this. Drop the 2, 4t plus 3, and the minus 4 goes away. Okay, this needs to be cleaned up a little bit. This is we've got a fraction going on here. This is going to be in the numerator, 4t plus 3 over, this is in the denominator, that 2, and this is in the denominator as well under a square root. Two t squared plus 3t minus 4. There we go. well, that's the first derivative. So, now, oh goodness, okay, gonna need more paper. Okay, we want to take the derivative of this function now, but it is a quotient now. So we need the quotient rule. The quotient rule says that if you've got a quotient of two functions of t or x or whatever you're dealing with, then the derivative will be the derivative of this times that minus that times the derivative of that all over the denominator squared. So let's see, if I wrote it as, let's see, just two arbitrary functions, f over g prime, that's going to be f prime times g minus f times g prime all over g squared. So here, now this g is not the same as that g. This is just some arbitrary denominator function that I chose here. Just so happens that they're the same letter. Okay. So I need to do the derivative of the numerator, which is just going to be 4, thank goodness, times g, which is the whole denominator, so 2 times the square root of 2t squared plus 3t minus 4, minus f, which is the top function, the numerator, 4t plus 3, times the derivative of the denominator. But we've already calculated that. We got this whole thing. Oh, this is going to be such a mess. I'm going to need more room. Okay, so I've rewritten it so I have a bit more room. Okay, so I'm trying to find the derivative of the denominator, which is this, but ignoring that too, we already have the derivative of this square root thing, right? That's what the original function was, and our derivative is this entire fraction. All I'm going to do is tack a 2 onto it, because this 2 is included in the denominator here. So I'll say 2 times this whole function here, 4t plus 3 over 2 times that big square root. And then all over the denominator squared. So squaring the denominator here, I'm going to have 4 times 2 squared is 4, and then squaring the square root, I'll just end up with 2t squared plus 3t. Now it's not under a square root anymore. And this is all I would want you to do. This can be cleaned up quite a bit more, especially with this radical and this radical being the same there. I know one's in the top, one's in the bottom, but things can be cleaned up here, but this setup would be just fine, especially for a problem like this, which is fairly complicated. Alright, 3 more.
You need me to stop?
Okay. Let's do another one. H of x equals 1 over 1 plus e to the 2x. Okay. Now we have a quotient here. But there's no function of x on the top, so we can just treat this like a chain rule, where the inner function is going to be the 1 plus e to the 2x, and the outer function is going to be 1 over x. So the derivative of the outer function is going to be negative 1 over x squared, but x is 1 plus e to the 2x, so all squared. That's the derivative of the outer with respect to the inner. And then times 1 plus e to the 2x. The derivative of that's a little mini chain rule there, right? So the derivative of 1 plus e to the 2x. The 1's going to go away. We need to take the derivative of e to the 2x. We actually did this one earlier, but remember that you would take the derivative of the outer function, which is e to the 2x, with respect to 2x, which is just that, and then times the derivative of the inner. And that 2 just ends up dropping down. So we have 2e to the 2x there. Cleaning this up a little bit, just putting this up here. Negative 2e to the 2x over 1 plus e to the 2x all squared. So that was my chain rule. Now, second derivative. The second derivative, we've got a quotient. So we're going to have, I'm going to scoot down a little bit. The derivative of this, how about this time with the quotient rule? Here's what I'm going to do. I'm going to write the derivative of that, so I haven't taken the derivative yet, I'm just setting it up, times the bottom, so 1 plus e to the 2x squared, minus, now I hold the first one, hold that numerator, don't take its derivative, and I multiply by the derivative of the bottom. Oops, let's see, that's not really what I meant to do. I meant to put the square on the inside. Okay. 1 plus e to the 2x squared, derivative of that, all over 1 plus e to the 2x all squared. So derivative of the first times the second minus first times derivative of the second all over the denominator squared. Now the denominator is already squared, you see that, so all that's going to happen down here is this exponent's going to turn into a 4. If you're squaring something that's already squared, the exponent will just turn into a 4. But that's not really, this isn't really the problem, it's all of this. So let's see, let's actually take these derivatives, this one and this one. So I'm going to back up my equal sign a bit. I'm going to go ahead and draw my fraction bar. I'm going to go ahead and say the bottom is 1 plus e to the 2x to the 4th, like I said earlier. Let's just get that out of the way. Okay, derivative of negative 2 times e to the 2x. Wait a second. Oh yeah, sorry, okay. Derivative of negative 2 times e to the 2x. Basically all that's going to happen is another 2 is going to drop down, so I'm going to have negative 4 e to the 2x, and then just times this mess here, which is going to be 1 plus e to the 2x all squared. That was the original denominator. Now I'm going to have plus, because negative, 2e to the 2x, and now I need to take the derivative of this. And that's going to be a chain rule inside of a chain rule. Not too bad though, because we know what's going to happen with this e to the 2x. It's just going to drop a 2, right? Alright, so I need to take the derivative of this whole thing. Let's do it down here. 1 plus e to the 2x all squared prime. Inner function is 1 plus e to the 2x. Outer function is the square. So how do you take the derivative of something squared? You drop the 2. And then with respect to the inner, that exponent is just 1 now. Now times the derivative of the inner, but what's the derivative of 1 plus e to the 2x? It's just 2e to the 2x. That's where the little mini chain rule happening inside of the bigger chain rule. So all of this goes right here. Better wrap it in parentheses. So 2 times 1 plus e to the 2x times 2e to the 2x, close the bigger parentheses. This could surely be cleaned up a lot, but this is fine. This setup is just fine. Alright. 14. K of x is equal to 1 over ln of x. Is this 14? Yes. Okay. K prime of x. Okay, I've got 1 over ln of x. I can think of 1 over ln of x as ln of x raised to the negative 1 power. So it's going to be a chain rule. Derivative of the outer function with respect to the inner, so the outer is that negative 1, so I'll drop a negative 1, and then times ln of x to the negative 2, right? That's the derivative of the outer function with respect to the inner, and then times the derivative of the inner function, which is the ln of x, and that's going to be a 1 over x. So what's happening here is inner is ln of x, and outer is x to the negative 1. Replacing that inner with just an x, we've got x to the negative 1. So the derivative of x to the negative 1, you drop the negative 1, take the exponent down by 2. That's how I got this. Negative 1 times, and then there's the exponent of negative 2. But remember, it's with respect to the inner function. So there's the with respect to the inner being ln of x. And then times the derivative of the inner. And the derivative of ln of x is just 1 over x. Okay, let's clean this up. Let's see, we can write it as negative 1 over ln of x all squared, right? Times 1 over x. Whoops, that means, oh shoot, the x will be in the bottom. There we go. Like that. Alternatively, we could write it as negative 1 times ln of x to the negative 2 times x to the negative 1, depending on if we wanted to write them with positive exponents in the denominator or negative exponents up top. Second derivative. Well, what's going to be easiest here? Probably looking at them this way over here in exponent form, negative exponent form, and thinking of it as a product rule. So remember, the product rule is going to be similar to the quotient rule. It's going to be derivative of first times second plus first times derivative of second, with no division bar in the product rule. So we're going to have, first of all, negative 1 times everything. That negative 1 is just going to be tacked onto the outside of the entire derivative. Derivative of the first, so negative 2 is going to drop down. We're going to keep that ln of x. Its exponent is going to drop, and then we're going to say times 1 over x. That's the derivative of ln of x all to the negative 2. That's the chain rule happening there. And then times another x to the negative 1. That's the first part of the product rule. Then plus, now I hold this function fixed, so ln of x to the negative 2 times the derivative of x to the negative 1 is going to be negative 1 times x to the negative 2. Now let's see, I've closed all of those, so now, there we go. Okay, and we can clean this up a little bit. Distribute, let's see, distribute this minus sign right here, so I'll have 2 times ln of x all to the negative 3. 1 over x, this is 1 over x, and this is also 1 over x, so I could say this is x to the negative 2. And then negative times a positive, but then there's another negative happening here, so that'll end up being positive. And then I'll have ln of x to the negative 2 times x to the negative 2. So again, can be cleaned up a lot, but this is fine. Oh, is that? Yes, there we go. There we go. It's pretty complicated, but remember that you can pause these videos and rework these at your own speed. And you can always ask me about them in the little comment section under these videos in Canvas. Last one. Let's say y is equal to square root of x times 1 plus e to the x. And let's find the second derivative of y with respect to x. So I'm using the equation notation, not the function notation, but it's definitely implied here that y is a function of x, because y is dependent on x. Okay, so first derivative, dy dx. Definitely going to use a product rule here. So I need the derivative of square root of x, that's going to be 1/2 times x to the negative 1/2, and then times that second factor, 1 plus e to the x. Now the second part of the product rule says I hold the first function fixed, and then I take the derivative of this, but derivative of 1 is going to be 0, it's just going to disappear, and derivative of e to the x is just e to the x. And there we go. That's fine right there. We could make this a little better, I suppose. Say this right here would be 2 square root of x in the denominator. So this 1/2 x to the negative 1/2, remember, turns into 1/2 times square root of x, and then I just threw that 1 plus e to the x in the numerator. Because they're being multiplied. These two things, this thing and this thing, are being multiplied. Okay, now second derivative. I need the derivative of this, so that's going to be quotient rule and then a product rule. So a lot of work here, but at least they're easier functions. The quotient rule will be the derivative of the numerator times the denominator minus numerator times derivative of denominator all over denominator squared. And then now this function plus square root of x, so now, derivative of, this one's easier. Let's just go ahead and do this one without setting up all the derivative notation. Derivative of the first is going to be 1/2 times x to the negative 1/2. It's going to look very similar to this, actually. And then times e to the x. That's the first part of the product rule. And then plus hold square root of x and take the derivative of e to the x, but that's just e to the x. So there we go. That's the product rule for this part already done. It was just much easier. I felt like it didn't need to be set up like the quotient rule needed to be. Alright, so now let's actually do these derivatives. So I've got 1 plus e to the x. The derivative of that is just e to the x because the 1 gets absorbed. So I've got e to the x times 2 square root of x minus 1 plus e to the x. Derivative of 2 square root of x is going to be 2 times 1/2 and then x to the negative 1/2. Now all over, squaring both of these, because they're connected with multiplication, I can actually distribute the square, so I'll have 4x. 2 squared is 4, square root of x squared is just x, and then plus this stuff. So this first one will be 1/2 square root of x, and then I can just throw that e to the x up top. And then plus square root of x times e to the x. And let's leave it like that. It can be cleaned up a bit. Well, actually it can be cleaned up pretty nice. We can say e to the x to e to the x square root of x, just putting the 2 up front because it looks a bit better, minus, now here, this 2 and this 1/2 will cancel, and this is going to be a square root of x in the denominator. And when I say the denominator, I just mean in this little fraction here. Still got the bigger denominator with a 4x in the bottom there. And then plus e to the x over 2 square root of x plus square root of x e to the x. It can be cleaned up more, but and in fact, if you, let me say something about these more. Oh god, I'm off camera. Dang it. There we go. Alright, let me re-say what I did there. From here to here, all I did was put the 2 up front and drop the brackets. From this to this, I threw the 1 plus e to the x in the numerator because, well, first of all, these 2's, the 2 and the 1/2 canceled. This turns into a square root of x in the denominator, and then I just threw this on top. And then big fraction bar and the 4x, and then these just came straight down. They didn't change. Now, if you want to, if you're working these and you want to plug them into Wolfram Alpha or Mathway or whatever you're using to check your work, I would definitely note that the online calculators that compute derivatives are going to simplify as much as possible, which I'm not doing because I'm not requiring you to do. I'm just requiring you to get the setup. Like this from number 14, this is just ugly. I mean, this can be cleaned up so much more. But I'm telling you that you don't need to do that. You just need to be able to set up and take the derivatives where appropriate. An online calculator would give you, like for instance, something like this would give you, what would it give you? 1 over ln of x times x all squared, and then 2 over ln of x plus 1. That's probably what it would give you, because they're going to simplify all the way, factor out common terms, so just keep that in mind. Now, homework for this section to look at is 1 through 9. Alright, you should find that if you could sit through problems 11 through 15 in this lecture, which are the harder ones, if you can sit through those and understand most of what's happening there, except for maybe some of the algebra gets a little weird, if you feel fairly confident about those problems, then these should be extremely easy. And anything that I throw at you on a test or homework should seem, in comparison, very easy. Alright, that is it. Well, that's it for the first section of 5.3.